Alright, so what we're going to do today is we're going to begin today's work with a warm-up problem that goes back to an idea that was covered in Chapter 2 that deals with solving for missing angles within parallel lines cut by a transversal. So if you have your notebook that you do your work on, you can open that up, and this is going to be a great warm-up problem to begin with. What I want you to understand in solving for these variables is that these angles next to each other, again, are called a linear pair. And they are supplementary with one another, meaning that they add up to 180 degrees. And so what that means is I can take 6x minus 4, and I can add that to 4x minus 6. And if I were to add those two together, those should add up to make 180 degrees. So if I solve for x, that's going to make 10x minus 10 equals 180. And I would add 10 to both sides, making 10x equals 190. And then divide both sides by 10, and I get that x is equal to 19 degrees. Or not 19 degrees, but just 19. So why that's useful is because now if I plug 19 back in for x right here, that's going to tell me the measurement of that angle. If I do 6 times 19 and then subtract 4 from that, 114, that's going to be 110 degrees. So the measure of that actual angle here is 110 degrees, which is very useful because y and this angle right here are the same because these, if you recall, are called corresponding angles. They are angles in the same spot of the two intersecting lines, and corresponding angles are equal. So that means that y is also equal to 110 degrees. And so this brings us back to some ideas that we've done quite a while ago with parallel lines cut by a transversal. And it's a very necessary problem to bring our eyes back to because we're going to continue to build on those ideas in addition to the problems with triangles as we move forward. Now what we're going to do is we are going to do one more problem dealing with probability. That's a warm-up problem. It says use an area model or a tree diagram to compute the desired probability. And so what I'm going to do is I'm first going to do an area model that would show us how this could work as an area model. I'm going to erase that actually. I'm going to make it a little bit larger if I can. Over here what we're going to do is we're going to have spinner number 1, and up here we're going to have spinner 2. And it does not necessarily matter which side you put each one on, but for spinner number 1, what we want to identify is that there are 3 different outcomes that we could get: red, blue, or yellow. So I'm going to put those associated outcomes here of red, blue, or yellow. I didn't really space this very well. And then I draw these 3 lines across. The probability of getting red, there are 3 R's there within the entire thing, so 3 out of 6 is the same thing as 1/2. The probability of getting blue is 2 out of 6, or 1/3. The probability of getting a yellow is 1 out of 6. Now on the second spinner, looks like we have again blue, yellow, or red. So I'm going to partition this again into 3 spots. So we could get a blue, we could get yellow, or we could get red, and the associated probability in the second spinner of getting blue is 1/4. Probability of getting yellow is also 1/4, and then the probability of getting red is 1/2. Now, as a brief reminder, in order to fill out the probabilities for getting, for example, in this box right here of being red, blue, that would be 1/2 times 1/4. I would multiply the 2 sides here together that make up the area of that rectangle, and that would be 1/8, or 0.125, or 12.5%. So this outcome here would be red-yellow, this would be red-red, this would be blue-blue, blue-yellow, blue-red. This would be blue-yellow, this would be yellow-yellow, and this would be yellow-red. So I'm going to pause the video and fill in the associated probabilities for that really quick, and then we'll answer some questions. Alright, so what I've done is I've filled in this table with all the associated probabilities and all the different outcomes. What I also want to highlight is I did a tree diagram down below. And the tree diagram is just another way of representing a probability area model. And again, the way that this works is this first dot represents our first spin, and that we have 3 different outcomes that we could get. And each of these branches just represent what each of the outcomes could be from that. So on our first spin, we could get a blue, a yellow, or a red. And from that, let's say I got a blue on the first one. That's a 1/3 probability on the first spinner. From that outcome, I could get 3 different outcomes on the yellow probability, hence the 3 separate branches and their associated probabilities. So if I got a blue and then a blue, the probability of getting that is found by taking this probability and this probability, which would be 1/3 times 1/4, which is equal to 1/12. And so that probability of blue is 1/12. That should match what we have in the table, which indeed it is. It's 1/12. And you could follow that same reasoning. What if I got yellow and then red? Well, yellow, red would be 1/6 times 1/2. So yellow, red is 1/6 times 1/2, which is 1/12. So as I look, and yellow, red in the table, is that 1/12? Yep, it is. So either a tree diagram or a probability area model would suffice. Either one is fine. It says in question 11, if each spinner is spun once, what is the probability that both spinners show blue? Well, both spinners showing blue would be this one right here, blue, which is 1/12, which is kind of cool. In question 12, if each spinner is spun once, what's the probability that both show the same color? Well, that would be blue, red, or yellow. And you would add up those probabilities together, which would be 2 24s and 4 24s, 6 24s. 7 out of 24 would be that probability. You could type that in. That's essentially adding each of those 3 together. 7 out of 24, a shade under 1/3. And so that's another way that we could use these area models to help us find certain probabilities. If you get to this point now, I'm not going to ask that you need to go any further into the idea of unions, intersections, and complements. This is a fun lesson to go through if you desire, but I'm not going to ask that we're going to do it. We're just actually going to refrain from doing section 4.2.4. So the homework for today is chapter 4, day 7 worksheet, and it highlights more practice of area models and tree diagrams. It has nothing to do with 4.2.4. So don't worry about doing the rest of this classwork, just those 2 warm-ups for today. If you do desire more information on how to do this, you can go to the very end of the lesson. And at the end of the lesson here, you can see the math notes for union, complements, and intersections. And then if you have any more questions, you can swing by the office hours, 11 a.m. to 12 p.m. every day. Thanks. Hope you are all safe and healthy. We'll talk soon.